Section 1.3 Atomic Orbitals. Let's look at the simplest cases first. The hydrogen atom and the hydrogenic ions. In a hydrogen atom, the energy of an atomic orbital is -1/2n squared. The unit is atomic unit of energy. It's 4.36 attojoule. N is the principal quantum number. Therefore, we can rewrite this into -2.18 attojoule per n squared for the hydrogen atom. For the hydrogenic ions, such as helium plus, lithium 2 plus, beryllium 3 plus, and boron 4 plus, we have a slightly different equation. This is -z²/2n squared, and therefore the energy is -2.18 attojoule times z²/n squared. For beryllium 3 plus, z is 4. For boron 4 plus, z is 5. Now you are looking at the energy levels of the atomic orbitals in the hydrogen atom. This is helium plus. Remember, in helium plus, there are 2 protons. The nuclear charge is 2. Therefore, if you see this -r here, this is -4r. What is r? R is simply -1/2 of a atomic unit. So this is the atomic orbitals of the hydrogen atom, or helium plus, or lithium 2 plus, and some other hydrogenic ions. So you have 1s orbital, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. If you look at this picture, you find 3s, 3p, and 3d with the same energy. We say they are degenerate. 3s, 3p, and 3d, the 9. 1, 2, 3, 4, 5, 6, 7, 9. These 9 orbitals have the same energy and thus are degenerate. They can accommodate a total of 18 electrons at most. For non-hydrogen atoms, such as helium, you will see the 2s orbital has a little bit lower energy than 2p. 3s has lower energy than 3p. 3p has lower energy than 3d, etc. Now let's look at shells, subshells, and orbitals. So first, shells. In a hydrogen atom, you have an infinite number of shells. N equals 1, 2, 3, 4, 5, 6, etc. Each corresponds to a shell. When N equals 3, you have 3 subshells. 3s, 3p, 3d. And we define a quantum number L. That's the angular momentum quantum number. L can be from 0 to n-1. So when n is 3, L can be 0, 1, or 2. When L is 0, 1, or 2, we have s, p, and d orbitals. Why is L called the angular momentum quantum number? This number can be used to calculate the angular momentum of the electron rotating about the nucleus. The equation is very simple. It's the square root of L times L plus 1 times h bar. This is the angular momentum of the electron orbiting about the nucleus. H bar is the reduced Planck constant, so it's h/2 pi. H is 6.626 times 10 to the power of -34 joule second. There's another quantum number, m sub L, that tells us the z component of the angular momentum. It's m sub L times h bar. So m sub L can be from -L to positive L. There's a degeneracy of 2L plus 1. For example, when L is equal to 3, that's an f orbital, M sub L can be negative 3, negative 2, negative 1, 0, 1, 2, 3, with a degeneracy of 7. Electron spin. Every electron rotates about its own center, or its own x, y, and z axis. It's also possible to calculate the angular momentum of the electron spin. It's a constant. It's square root of 3 over 2 times h bar. The equation is the square root of s times s plus 1 and then times h bar. This s is the spin quantum number. It's 1/2. So you plug in 1/2 into this equation, you'll get the square root of 0.5 times 1.5. That's the square root of 3 over 2. Finally, there's the last and fifth quantum number, m sub s. That's the z component of the angular momentum of the electron spin. And that z component is always positive or negative 1/2 h bar. So this m sub s is plus minus 1/2. The z component is plus minus 1/2 h bar. You can imagine a 3D vector whose length is the square root of 3 over 2. That's the electron spin. Its z component is plus minus 1/2, and that means this vector can point up or down, and at the same time it's pointing into the x and y directions. Now let's look at the shapes of the atomic orbitals. First, let's look at the nodes. An atomic orbital always has n-1 nodes. Among these n-1 nodes, there are L planar nodes and n-1 minus L spherical nodes. So this L plus this n-1 minus L, you get the total number of nodes. So for 1s orbital, n is 1, 0 node. 2s, 2p, 1 node. 3s, 3p, 3d, 2 nodes. 4s, 4p, 4d, 4f. They all have 3 nodes. Now let's look at the planar nodes. Of course, there's a 0 node here. 2s and 2p, they're different. In a 2p orbital, there's 1 planar node. In the xy plane for pz, in the yz plane for px, in the xz plane for py. In the 3s, 3p, 3d orbitals, there are 0, 1, and 2 planar nodes, respectively. 4s, 4p, 4d, 4f, again, the number of planar nodes is equal to L, this angular momentum quantum number. And then the first column here minus this column, you get the number of spherical nodes. It's n-1 minus L. Therefore, if you have a 2s orbital, this is the total number of nodes. It's n-1. And then subtract the number of planar nodes. You have a spherical nodes here. For 2p orbitals, there's no spherical nodes. For s, 3 spherical nodes. For p, 2 spherical nodes. For d, 1 spherical nodes. For f, 0 spherical nodes. Now let's look at the pictures to count the number of nodes. 1s, 0. 2s, if you look at the red and the green, there are different phases, there are different signs. Between red and green, there's a node. Between red and green, there's a node. Between this green and this red, there's another one. 2 nodes, 3 nodes, 4 nodes, 5 nodes, 6 nodes. The number of nodes is, again, n-1. 2p orbitals. 2p orbitals, each of them has 1 node, and it's planar. 1, 1, 1, 1 planar node. 3p. Now n is equal to 3. There are 3 minus 1 equals 2. 2 nodes. We should be able to find 2 nodes in each of the 3p orbitals. So the first node over here, planar, planar, planar. You can cut this 3p into 2 halves. That's planar. And also, there's a spherical node surrounding the smaller 3p shape orbital. So over here, you just draw a sphere surrounding the smaller one. Again, over here, same thing. 3D. In a 3D orbital, there are 2 planar nodes and 0 spherical node. So if you just look at this one, you can see there's a node over here. Between the red and the green, there's 1. Okay? This 1. And then there's another one. Okay? These 2 nodal planes are perpendicular to each other. Okay, same here. 2 spherical planar nodes perpendicular to each other. Same here. This one is a little bit different. This one, you can identify 2 cones. So 1 cone here, just like your ice cream cone. 1 cone here. Surrounding the green area, there's a cone. There's another cone. Okay. And then in the 4D orbitals, there are a total of 3 nodes. 2 planar nodes and 1 spherical nodes. So over here you can find 1, 2, 2 planar, 1, 2, and then the spherical nodes, enclosing the smaller D-type orbitals here inside. This is the smaller one. For the F orbitals, you can find this is 4F, so 3 nodes, and all of them are planar. So again, you can do this 1, 2, 3. 5G 1, 2, 3, 4. 4 nodal surfaces. 1, 2, 3, 4. 4 nodal surfaces in the 5G orbital. And those 4 nodal surfaces are all planar. Now let's look at some mathematics. This is just the polar coordinates. If you have a data point over here, you can use x, y, and z, referring to the position of this data point over here or this electron. But also you can use the so-called polar spherical coordinates. You have r, that's the distance between this electron and the center. And also you have theta, that's the angle between this r and the z-axis. And then you have this phi. Phi is from 0 to 360 degrees. That's this vector rotating about the z-axis. So r is again the distance between the electron and usually the nucleus. Usually we put the nucleus at the center. Theta corresponds to the latitude of Earth, and phi is the longitude. Now let's look at the radial variation of atomic orbitals. So we can use a wave function to describe the atomic orbital. The wave function contains 2 terms. One is the radial part, one is the angular part. The radial part contains only one variable r. The angular part contains theta and phi. So if we look at the radial part, we can see in the hydrogen atom, the radial part of the wave function is a product of a polynomial function and an exponential function. The polynomial function has an order of n-1. For example, if we look at this 1s, 2s, and 3s orbitals. First, the polynomial function has an order of n-1. So in this case, you have a polynomial function of an order of 0, 1, and 2. 0, 1, and 2. And then multiplied by exponential function. In a hydrogen atom, the 1s orbital has this e to the power negative r as the exponential function. It decays as r increases. This one is e to the power negative r over 2. This 2 is the principal quantum number. So here, e to the power negative r over 3. What about the 4s orbital? It's just a polynomial function of r of an order of 3 times e to the power of negative r over 4. And look, this r is not in meters, of course. It's in atomic unit of length. 1 atomic unit of length is 0.529 angstroms. And 1 angstrom is 10 to the power of negative 10 meters. So if we set these equations to 0, we'll be able to find the spherical nodal surfaces. For example, this one does not have a nodal surface. This one has one spherical nodal surface when r is equal to 2. When r is 2, this is 0. The probability density is 0. We cannot find the electron there. At r being equal to 2 atomic unit of length. This one, we just solve this second order equation. We get 2 roots or 2 solutions. R can be 1.9 or 7.1. When that's the case, we have 2 spherical surfaces. One has a radius of 1.9 atomic unit, the other 7.1 atomic unit. How do I solve this second order equation? Well, I use Wolfram alpha. So what you can do is you can just click this link and see this is the equation. The answer is given down there. R is 4.5 plus minus 1.5 times the square root of 3. So 2 solutions. 2 nodal surfaces. So this shows you the number of nodes. 1s, no node, 2s, 1 here, 3s, 1 here, the other one here, 2 nodes, 4s, 3 nodes, 5s, 4 nodes. Now the radial variation of the atomic orbitals. Now let's look at the radial part of the p orbitals. So we talked about the s orbitals, and now this is about the p orbitals. And again, the radial part is still a polynomial function times an exponential function. So for example, 2p. The 2p wave functions are x times e to the power of negative r over 2, or y times e to the power of negative r over 2, or z times e to the power of negative r over 2. So we wonder, what's the radial part? Well, because if we do a conversion from the x, y, z Cartesian coordinates to the polar coordinates. So I made a mistake here. I need to fix this mistake. This is y. And then we have these equations. And when you look at these equations, you realize this x, y, z can be expressed in terms of r, theta, and phi. And conversely, r, theta, and phi can be expressed as a function of x, y, and z. So in this case, x is simply r times sine theta times cosine phi. Therefore, the radial part is r times e to the power of negative r over 2. Same here, r times e to the power of negative r over 2. Same here. So you have radial part. If you look at 3p, well, again, you have a polynomial function of r. In this case, it's second order. You're looking at 6 minus r times this x is r times sine theta times cosine phi. So you can view this as a product of the radial part and the angular part. The radial part is 6 minus r times e to the power of negative r over 3. Sometimes we use a hybrid expression because it's convenient. So over here, you see r and you see x at the same time. X is from the xyz Cartesian coordinates. R is from the polar spherical coordinates. Why is this convenient? Because you can immediately see when x is 0, you have a nodal surface. When y is 0, you have a nodal surface in py. When z is 0, you have a nodal surface in pz. And when x is 0, y is 0, or z is 0, you see a planar nodal surface. Or in the 3p orbitals, r can be 6. When r is equal to 6 atomic unit, you have a spherical nodal surface. So let's look at the radial part. Again, for the 2p orbital, there's no spherical node. There's a planar node, of course. In the 3p orbital, there's a planar node, and also there's a spherical node with a radius of 6 atomic units. So this is wrong. So they marked this wrong. She should be somewhere around here. 6 atomic unit. This A naught is 1 atomic unit of length, is 0.529 angstroms, is 0.529 times 10 to the power of negative 10 meters. The radial distribution function, it's different from the wave function. The radial distribution function is how the probability density of finding the electron depend on the radius. So it's actually 4 pi r squared times psi squared. And this psi is the radial part of the wave function. So it's not just the psi, it's psi squared, and then multiplied by 4 pi r squared. The reason is, in quantum mechanics, a wave function does not have any physical meaning, but if you square it, that's the probability density of finding the electron. Or you can say probability per unit volume. So that's the physical meaning of psi squared. All right, and then if we are looking at a atom or atomic orbital, the volume of the shell between radius r and r plus dr is 4 pi r squared times dr. You can prove this. This is the surface area of the sphere or the shell. This is the thickness of the shell. Therefore, the probability of finding the electron in that shell is 4 pi r squared times psi squared times dr. So in this case, we can tell between r and r plus dr, the radial distribution is this part, 4 pi r squared psi squared. This is important because when r is 0, the distribution function is 0. Sometimes we drop this 4 pi because it's just a constant. With or without 4 pi, the shape of this distribution function is the same. Now let's look at the distribution function for 1s, 2s, and 3s. Look, when r is 0, this distribution function is 0 because of that r squared term. So let's look at this function again. Look at this function, it's 4 pi r squared times psi squared. So when r is 0, this function is 0. And this psi is e to the power of negative r for the 1s orbital. It's e to the power of negative r over 2 for the 2s orbital. And e to the power of r over 3 for the 3s orbital. So that's why you see this kind of shape. It goes up and goes down. There's a maximum because the function is r squared times e to the power of negative 2r. Again, the 1s wave function is e to the power of negative r. But psi squared is e to the power of negative 2r. And then we need to multiply this 4 pi r squared. So this function is 4 pi r squared times e to the power of negative 2r. You can take its first derivative and set it to be 0 to find this maximum here. Similarly, if you look at the 2s orbital, it's simple. We have a 2s orbital. The distribution function is r squared times 2 minus r squared. Okay, so the reason is in the wave function of 2s, you have a polynomial function of 2 minus r. And then times e to the power of negative r. E to the power of negative r is actually e to the power of negative r over 2 squared. Now 3s. Alright, so remember the wave function of 3s is 27 minus 18r plus 2r squared times e to the power of negative r over 3. So you need to square that, and then the result multiplied by r squared. You get the distribution function of 3s. So again, I just want to show you this is the radial part of the wave function squared. It decays exponentially. For the 1s orbital, it's e to the power of negative 2r. For the 2s orbital, it's e to the power of negative r. For the 3s orbital, it's e to the power of negative 2r over 3. Alright, and then this is r squared. It goes up. Therefore, if you multiply r squared and the radial part squared, you see a maximum. This is the comparison between 2s and 2p, and later you will see the so-called penetration effect of the 2s orbital. You see a significant probability of finding the 2s electrons very close to the nucleus, and then the attraction between the nucleus and the 2s electrons is greater than the nucleus between nucleus and 2p. The angular variation. So now you are looking at a s orbital. So this is the 1s orbital. It's spherical. It does not depend on theta and phi. You cannot see theta or phi in the wave function in the 1s orbital. It's e to the power of negative r. You cannot see theta or phi in the 2s orbital either. That's 2 minus r times e to the power of negative r over 2. This is the 2p orbitals. The wave functions are here, x times the exponential function, or y or z times the same exponential function. Look at the nodes. When x is equal to 0, you have a planar node here. When y equals 0, you have a planar node here. When z is 0, you have a planar node over here when z is 0. And then you have positive phase, negative phase. For example, if you look at 2pz, when z is positive, you have a positive phase. When z is negative, you have a negative phase. Now let's look at the 5d orbitals. The 5 3d orbitals have this kind of form. Again, each of them contains e to the power of negative r over 3, and then multiplied by a polynomial function of r. And then there's a theta and phi contribution as well. So for example, let's look at this one. This one is pretty simple. This is dx squared minus y squared. So the polynomial function is x squared minus y squared. And if you set this to be 0, x is equal to y, or x is equal to negative y. Therefore, you have two also planar nodes. One is x equals y, the other is x equals negative y. And then if you look at 3dxy, it's different. In this case, when x is 0, you have a nodal surface. When y is 0, you have a nodal surface. So this nodal plane contains two axes. This nodal plane also contains two axes. So this one corresponds to x equals 0, and this one contains the y and z axis. This one corresponds to y equals 0, so this one contains x and z planar nodal surfaces. Same for this too. This one is quite different. This is because if you look at the wave function, it's 3z squared minus r squared. So the nodal surface is z is equal to plus minus 1 over square root of 3 times r. Another way to look at it, z is r times cosine theta. So really it's just cosine theta is equal to plus minus 1 over the square root of 3. So theta can be plus minus 50 something degrees Celsius. So this is theta equals plus 50 degrees Celsius. This is theta equals negative 50 something degree. I'm sorry, I shouldn't say Celsius. Okay, theta is 50 plus degrees. Theta is negative 50 degrees. F orbitals. So you are looking at 4 F orbitals, not 5 F orbitals. The reason is I can see 3 nodal surfaces. each orbital. So 1, 2, 3. 1, 2, 3. Alright, so if you see 3 nodal surfaces, well, apparently n is equal to 4 because the number of nodal surfaces is n minus 1. Right, you have 7 f orbitals.